So this is what we were talking about. When we were talking about transmissibility ratio, and we said there are two cases. One is the force transmitted the other one is the effect of displacement transmitted. So this is case one, this is case two. So in case one, we had basically a system that is acted upon by a force, and we want to reduce the impact of this forcing function. For the time being, of course, we are assuming that it's a harmonic forcing function. We want to reduce the effect of that on this foundation or on the system, right, that is supporting this force. This force can be a rotating machinery force. We want to reduce the effect or the adverse impact of this on the foundation. So we said the force transmitted was Ku plus Cu dot, and as we saw, the transmissibility ratio, which is what we want to reduce, that was maximum force transmitted to the maximum force applied, okay? We plotted that, we derived that, and we plotted it, and it was, and remember that we're talking about the case that zeta is less than 0.707. Because if zeta is greater than 0.707, we know that the maximum dynamic displacement will always be less than the static displacement anyway. So we don't care about that. This is the case that we are concerned and want to know within that range what happens. And this is for the force transmitted. As we saw, we had basically something like this. As we reduce we increase the damping ratio that's what we observed. So the observation that we had was, first of all curves go through R is equal to square root of 2, okay? They intersect at that point. The second observation we made was if R is greater than the square root 2, which is what we ideally want, because less than square root of 2, no matter what range of frequency ratio you are, the transmissibility ratio is always higher than 1, which is not really desirable, right? So first of all, you really want to make sure that transmissibility ratio is greater than square root of 2 by choosing the right stiffness, right support system. But even within that range, okay, as you increase now the damping, as you can see, okay, this is 0.1, 0.2, 0.3. Damping, increasing damping ratio has no effect on reducing the transmissibility ratio. In other words, in fact, as you increase the damping, transmissibility ratio goes higher. So beyond this range, damping is not the way to increase in order to reduce the effect of, or the adverse effect of this force. Another observation we made was, you really want, ideally, that R be greater than square root of 2. So that means what? That means omega is greater than omega n square root 2, or let's say omega n is what? 1 over square root 2 of omega. If omega is constant for a certain case, right, you want to do what? You want to increase R, right? If you increase R, that means you're reducing this, right? So in other words, to reduce transmissibility ratio, you want to have as big of an R as possible. That means you need to reduce the frequency of the system, natural frequency of the system. Or in other words, you want to reduce K over M. Mass, you don't have much control over it. So you want to reduce K then, right? So the most effective isolation system, the most effective stiffness for the system that would reduce the effect of, that would reduce the transmissibility ratio is when you have a soft stiffness, or as small of a stiffness as possible. So a soft system is the best system for vibration isolation. But what happens, is a give and take, right? What do you compensate instead of that? And you get a large static displacement, right? Because static displacement is weight over K. So if you reduce this, your static displacement goes higher. So vibration isolation is a balancing act that you need to find out what is your optimum stiffness value. With damping is clear. Damping, you saw that. For vibration isolation, if you're beyond this, in fact, increasing the damping doesn't do you any good. So if you consider just a particular case, you want to reduce the transmissibility ratio, the way to do it, just going further and further here, which means reducing K. So let's do we did an example problem on this or no? So let's do an example problem before I get to the second case, which is the displacement transmitted. So I'll do a simple problem. Let's say you have, say, a rotating machinery okay, that weight of the machine, okay, the rotating machinery weighs 2,200 pounds, okay, which is pound force, right? We have an unbalance of 1.33 inch ounce. That means at 1 inch radius, this is 1 inch, and the weight of this unbalanced mass is 1.33 ounce, or is 1.33 divided by 16 pounds, right? And the machine operates at a frequency of 7,200 RPM. Okay. What the criteria that is given to you is that you want to make sure that the force transmitted over, let's say, in other words, let's phrase it like this. Design an isolation system that assures the force transmitted is less than 50 pounds. So that's the criteria that you've been given. You have been given this heavy piece of machinery, it operates at that frequency, has a rotating unbalance, and you are concerned about what kind of beam you need to support this machine in such a way that you know that this beam cannot handle more than 50-pound force maximum, otherwise its displacement is going to be very large. So you want to keep the force transmitted less than 50 pounds. And let's say, for this case, consider the damping ratio is actually 0. So the transmissibility ratio, or the absolute value of that is 1 minus r squared, or you can write that as 1 r squared minus 1, doesn't matter if you're looking at the absolute value. Okay, so let's solve the problem. What is the transmissibility ratio? Is maximum force transmitted, right, to the maximum force applied. So what is the maximum force applied? Maximum force applied is the rotating unbalance, right? So what was the right-hand side of the equation? Yeah, in other words, F0 sine omega t. What was F0? Was m sub e times e omega squared. So what you need to find is find the maximum force transmitted, which is 50, right, divided by me omega squared. You want this to be less than 1, right? That's what you want. So, or it's been given that this is less than 50 or greater than 50. Okay. So let's evaluate this. This is 1.33 divided by 16. This is in pound. You need to convert that pound force to pound mass. So that's ME. When the problem states 1.33 ounce means this is 1, so this is 1. What is the frequency? Frequency is given as 7,200 RPM. So you need to convert that to radians per second, 2 pi over 60. That will be 754 radians per second. So this is 754 squared, okay? But this is obviously equal to 1 over r squared minus 1, right? So you want to find r, basically, right? Or natural frequency of the support system. So if you do that, you have then, this comes out to be, this value comes out to be 122.7 pounds. So 50, okay, divided by 122.7 is 1 over r squared minus 1. If you solve this, you see that r comes out to be 1.86 radians per second.
Yeah, ratio. So it should be unitless, right? Because it's omega.
Oh,
omega.
so sorry. That would be
No units.
that would be ratio. So r is omega over omega n. You have omega 754, right? R is 1.86. that will give you omega n, that comes out to be 405.4 radians per second. So in order to have a force transmitted to the system be less than 50, your support system, which is this, should have a natural frequency less equal to 405.4. But 405.4 natural frequency is what? K over M. Mass of the system, you calculated it, I mean, it's given. Mass of the system is 2,200 divided by 386. Omega n is 405.4. You get the stiffness, that comes out to be 9.37 times 10 to the 5 pound per inch. So in order to really prevent this machine from failure or keep the force transmitted to this beam less than 50, you need to have this beam, you need the beam to have a stiffness of this value. However, we are not done yet because, you know, as I said, vibration isolation is a give and take. You want to make sure if you have such a stiffness, you really don't get a lot of static displacement. So you need to evaluate the static displacement for that beam, which is what? Is basically the weight of the system divided by that stiffness. Weight is 2,200 pounds divided by that 9.54 times 10 to the 5. That will give you a displacement of 2.3 times 10 to the negative 3 inches. So, which is good, because it's it's almost negligible. So, if you choose that as stiffness, the displacement is within the range that is acceptable. The system is not going to experience a large static deformation. So, any questions? Let's do another problem. Okay. 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 E is given as 1 inch. When it says unbalance of 1.33 inch ounce, means assuming that the unbalance is at a 1 inch radius from the center of rotation. That's the meaning of it. That's why E was 1. Any other questions? So let's do another problem. You have a beam or a system and again you have a machinery here. The beam's property are given 30 times 10 to the 6 psi. I is 120 inch to the 4, okay? So this system that is sitting on this beam is basically a machine that basically has a piston going up and down. It generates the machine, okay, generates a harmonic force that its amplitude is 7,000 pound, and operates at a frequency of 60 radians per second, okay? Let's say the system also has a damping of 10%, okay? What we want to find is, first, the amplitude or the maximum displacement of the motion caused by this rotating machinery. Yes,
F naught is 7,000 or 700?
7,000. I should have done a better job. Okay, 7,000. So we want to find the amplitude of the motion, and two, we want to find the force transmitted to the beam, which is this foundation. Okay. So basically what you have here is something like this. You want to find this force that these two, the spring and the damper, are going to be subjected to. That's what you want. First, you want to find the maximum displacement that this experiences, and the second, the force. So, obviously, this is simply supported beam, so the stiffness is what? 48 EI over L cubed. Length was given. Okay, I think length is given somewhere. Okay, and the weight is also given. The weight is 3,860 pounds. You need that, okay? So if you, and length is given as 10 feet, I think. If you calculate that, it comes out to be 10 to the order of power 5 pounds per inch. So the natural frequency of the system, which is K over M, would be 3,000, 10 to the 5 over 3,860 divided by 386 would be 100 radians per second. Zeta is equal to 0.1. Okay, so radius, ratio of the forcing frequency over natural frequency is 0.6. So the maximum amplitude, part one, the maximum amplitude that this is going to experience would be F0 over K times H. F0 is given 7,000 pounds. Okay, so over K, so that's 7,000 divided by K, 10 to the 5, okay, times 1 over 1 minus R squared plus 2 zeta R squared, okay. So you substitute for R 0.6, you see that U max comes out to be, okay, 0.1075 inches. So that's the maximum, yes?
Is the damping actually 10 or is it 0.1?
It's given as 0.1. Right.
Okay.
Right, it's given.
Is that not 10?
Oh, this 10%.
Okay.
Right, 10%, which is 0.1.
Oh, I thought you were just trying to say that was.
Oh, no, 10% damping.
10%.
Yeah. So when they tell you to consider 10% damping, that damping ratio is 0.1.
Right, yeah.
Okay. So that's the maximum displacement that the beam will experience. But let's see that if you allow that kind of a displacement, how much would be the force transmitted? Okay, so the transmissibility ratio is what, 1 plus 4 zeta squared r squared divided by 1 minus r squared plus 4 zeta squared r squared. Okay, zeta is 0.1, r is 0.6, so if you find transmissibility ratio would be 1.547, okay? So this is the ratio of the maximum force transmitted to the maximum input force. So what the problem is asking is to find the maximum force transmitted. So the maximum force transmitted then would be 1.547 times the input force that is given as 7,000. So that would be 10,827 pounds. So, which is interesting that you can see that for machinery that weighs about 3,800 pounds, if it operates at this frequency, right, the force that actually the system is going to experience is what? Almost 3 times higher than the weight of the machine. Okay? So be careful when you put too much load in that laundry machine, that how much force is gonna, depending of course, what kind of foundation this is sitting on. So when you go and buy some platform, don't just consider the weight of the machine. You need to know its frequency of operation to actually know how much force it exerts on that foundation. Okay. So simple little problem, but I thought would be practical. Okay. So now let's consider the second case, right? Second case being that if you had the input displacement. I'm not going to spend much time on that because, as you will see, we'll see a very interesting observation. That is, if you now consider a force instead of a displacement instead of a force acting on the system, this is what you will get. You will see, okay? That for the displacement case, okay. Let's see if I can find it here. So let's say for the displacement transmitted, let's say you have, consider this case, relative displacement. You have negative m y double dot, okay? That's the case when you have an input displacement and you want to find transmissibility ratio that is maximum displacement transmitted to the maximum input displacement. So if you consider a special case, because we haven't seen any other case for the input displacement except harmonic force for the time being. So if you assume the displacement is harmonic of this form, the right-hand side would become what? This becomes m omega squared sine of omega t, taking the second derivative of this, right? Which would be omega squared sine of omega t. So this becomes your forcing function for the right-hand side. So, as you can see then, this is, and let's consider this had also some amplitude, okay? So I will put some amplitude here too. So this is F0. So you do the same thing, okay? Your U, in this case, would be F0 over K, right? Times H sine of omega t minus theta, where F0 over K is this is F0 over K. So in other words, this would be M omega squared Y divided by K, okay, times H sine omega t minus theta. So that is the displacement, right? So this is the maximum, you want to find the maximum, again, displacement that these two go through. So if you add these up, in other words, do the same process of finding basically the maximum displacement that is transmitted, right, to the system, which would be the displacement due to y, okay, which is m omega squared, and displacement due to this, right, which is u, which is f0, this m omega squared y over k times h, okay? So this is the summation of these two, right? If you do that, then go through the same process. I'm not going to go through all the details. You will see amazingly that the transmissibility ratio that you will derive would be an identical expression. So I'm not going to go through that derivation because that's just a mathematical practice. That's what we need eventually, right? So you end up with exactly the same expression. In other words, the transmissibility ratio function that you end up with would be exactly the same. It doesn't really change. So that if the function that you would be plotting would be identical to the case of the force transmitted in the system. Therefore, whether you are dealing with a input force on the system or the input displacement of the system, this is the guiding principle. This is the criteria in order to reduce the effect of the vibration, or in other words, to design a vibration isolator, which is basically this K. That's what you need to use. Of course, for each given case, the criteria that is given obviously is different. Like the first problem, you may be given a criteria that you want to limit the force transmitted, and then based on that you find the stiffness. Or you're just having a problem, you really want to find the maximum force transmitted or the maximum displacement transmitted and find this ratio and see what you can do to keep this obviously less than 1. Because that's ideally what you want to do, keep this less than 1. But that's basically the concept of vibration isolation, okay? So with this said, believe it or not, we are done with harmonically excited damped systems. So we're not done yet with the force vibration, but we're done with harmonically excited damped systems. Okay. So what did we cover? I actually had a summary of that. It may not be a bad idea to summarize that here. This is what we covered, right? So since this was a broad topic that we studied first, we did what? We looked at this problem. F of t is f0 sine omega t, okay? And we studied the frequency response function, and one of the interesting outcomes was that we looked at basically this problem, right? Okay. So that's the frequency response function. The second case we looked at in this topic was rotating unbalance. And one of the important conclusions that we reached was the effect of rotating unbalance, which was basically can be described by this pseudo frequency response function. So that's the second topic we studied. The third topic we studied was input displacement. And we considered a special case only, a special case, where y, for instance, is something like this. The input displacement is harmonic. The fourth topic we studied was the transmissibility ratio. One of the topics we studied in between was the evaluation of damping, okay? So I'm not sure if we're going to consider topic 5 or whatever. So we introduced the concept of Q, that basically what it is given the frequency response function, if you can plot that and find the maximum value of this frequency response function, this is almost 1/2 zeta, okay? And you can evaluate the damping in the system. So in order to completely bring this to the closure, let's look at another approach for finding the damping ratio also, which is also similar to this, but is more popular. And that is called half, it's called half power method. And let's see how we can find the damping ratio using that approach. And the reason I'm focusing on this is I want to start the next topic fresh from on Monday, okay? Usually what, in order to find the damping ratio, it is not easy to, because the full frequency response function is not as nice and smooth as you can see like this. It is maybe something like this, okay? So, of course, one way, you can look at it and say, okay, I take some estimate here and take some average where that peak is. But since this is not very accurate, this is what is usually done. We will use this approach. We say, okay, let's find, okay, the value of this at 1/√2 of the peak. Let's say this line represents, in other words, this line represents 1/2 of H max, okay? If we can find this line, so that's the question. Let's say, assume that we can find that 1/2 H max, and draw this line, and find these two frequency ratios that correspond to that. We want to demonstrate how by, instead of that peak value, by using these two, which are easier to find, because usually this is smoother here, so drawing this line is easy. So we want to see by finding these two, how we can find the damping ratio. So let's do this. Let's assume that basically the R values that we want to find, okay, correspond to this. In other words, let's assume that we have 1/√2 times the maximum value, which we know is that Q value, that's what we call Q, is, okay, what? In other words, this value corresponds to what we want to find. In other words, would be the solution of this. Let's say those R values that we want to find are these. So in other words, what we want to find is, okay, we have the left-hand side given, which is the value of H. We want to know for this value of H, right? In other words, this line intersecting these two, what are these? These two would be the roots of this equation, okay? So if you rearrange that, you get R asterisk squared comes out to be 1 minus 2 zeta plus and minus 2 zeta 1 plus zeta squared. If you square these and do some algebraic manipulation, this is what you end up with. So in other words, the root 1 squared comes out to be 1 minus 2 zeta, 1 plus zeta squared minus 2 zeta squared, or 2 squared would be 1 minus 2 zeta, 1 plus 2 zeta, 1 plus zeta squared minus 2 zeta squared. Okay. If you look at these two, what we want is we want to find R1 and R2. Okay. If you look at that R1 and R2, those two roots, if you add those two, you see that R1 squared plus R2 squared would be 2 minus 4 zeta squared. Or in other words, zeta squared would be 1/4 of 2 minus R1 squared plus R2 squared, okay? Or zeta is 1/2 of that, 1/2 of that radical, R1 squared plus R2 squared. Obviously, this is not very interesting because we don't want to really go through such a complex relationship, using this complex, expression to find zeta. So we say that, okay, if damping is very small compared with, or in other words, much less than 1, you can see that this is almost 1 and this is almost 1. So if you add those two, okay, in other words, R1 squared becomes 1 minus 2 zeta minus 2 zeta squared, and R2 squared would be 1 minus 2 zeta, 1 plus 2 zeta minus 2 zeta squared. So now if you add these, R1 is almost 1 minus zeta minus zeta squared, because that damping is very small. So, and R2, okay, squared is 1 plus 2 zeta minus 2 zeta squared, okay? Oops, I'm sorry, 1 plus zeta, okay, minus zeta squared. In other words, if I actually, okay, if I find R, R1 and R2, which would be a square root of these, because if you approximate that square root, you end up with something like this. So if now you add these two, you see that zeta becomes 1/2 of R2 minus R1. This is the expression that is typically used to find the damping ratio. Okay, so what you basically do, you try to roughly consider 1/√2 of this peak, approximately. You cut this curve, you find these two roots, you just measure those. Damping ratio would be the difference and related to these two frequencies. So that's another way to evaluate the damping ratio in a system, which is based on the power of the system. We don't get into that, and it's called half-power method, but that's really the practical way to find the damping ratio in the system, in addition to that, using that Q approach. So with that said, we are done with the forced harmonic vibration, and we will start the periodic vibration next time. Have a great weekend.